Okay, hey guys, sorry the ending of that last video was a little bit rushed. One of my videos actually got flagged for copyright infringement because my roommate was playing music. So that's why I have a copyright strike and I can't make videos that are longer than 15 minutes anymore. And that is also why all the videos are public now. Normally I would keep them unlisted, but can't make them public. So basically, the idea behind this one, I rushed over this very quickly, but whenever you have only when your moment does not change sign, you should only have single curvature. So you can kind of see that here, that this is a single arc. This is a single arc. There's no double curvature. That is because my moment diagram does not change signs. Moment diagram, it looks odd, but it doesn't change signs. The only other thing to keep track of is that this must always be a right angle. So if I'm pushing this, you guys agree that the original force is being applied to the right? Like there's no possible way for this arm to move that way, right? It has to move that way. If it has to move that way, then this point has to rotate with it. This is being deformed counterclockwise, so the top part also has to be deformed counterclockwise, and that is why this point will end up going downwards. Because this has the same, these two sides have to have the same curvature as well, so they're both, you kind of see that they're both, I don't want to say they're concave downward, but because it doesn't really make sense for this one, you can kind of see that they're shaped the same way. They are not shaped like this. That is not how you get a moment diagram for this problem. Or deflected shape for that problem, this problem. Okay, so that is problem one. And let's get on, let's move to problem two now. Problem two will be easier. The only difference between problem one and problem two is that your load changes. This one was top heavy, this one is bottom heavy. And I just want to show you that it doesn't matter. You can take your cuts the same way, you're just going to be working with different sections. So I'm just going to look at the vertical member for this problem. And I'm going to look right here. Now, I could either work with the bottom half or the top half. I think in one of the videos I said it is easier to work with the bottom half, but I have since been proven wrong, and it is actually going to be easier to work with the top half. You can work with the trapezoidal load, but you get just as many terms as if you had done it with the other, as if you had done it in the other direction. So really quickly, I'm going to give you your reactions. I believe that it's always good for you to be able to just have your reactions, because if you don't have the right reactions, then your entire problem is going to be thrown off, and the reactions, changing your reactions is a very bad place to start off at. Okay, so you have some, you're going to get basically twice the vertical forces that you had before. And again, I'm not going to derive these. The derivation is very similar to what we did last time. Like I said before, I'm going to take a horizontal cut here. Horizontal cut in the vertical member. And yeah, horizontal cut in the vertical member. And I'm going to look at this part. If I do that, then when I draw this, I end up getting something that looks like this. And I'm going to make my x direction going this way. If I do that, then I have a normal triangular load, right? My triangular load is exactly what we had before. My Wx is going to be equal to W on L times x. And I can solve this exactly like I did before. The only difference now is that I'm gonna make my positive arrows slightly different. I find it easier to work like this. This will be my A of x, V of x, M of x. And I have a negative WL on 2 here, and a negative WL on 6 here. And I can do my equations just like I normally have done them before. My A of x is going to equal CY equals negative WL on 6. So I skipped a step here. Negative A of x plus CY equals 0. That gives me this. My next one, my shear. So let's do shear next. Let me bring this downwards again. If you guys saw how this camera is actually being held up, I don't know if you guys noticed, it's actually absurdly difficult to find a camera that can look downwards. Like, where do you put the camera? I was struggling with that for such a long time, but so my shear, Wx times x divided by 2 plus C of x equals 0. This is my sum of forces in the in the x direction. Sorry to get shear because we're working with a vertical member. My V of x is going to equal negative WL on 2 plus WX squared on 2L. Finally, my moment diagram, my moment equations. This is force, this is distance, this is moment, minus Cy times 2L plus Cx, Cxx, sorry, yes, equals 0. And I do this, and I solve everything for m of x. M of x is equal Okay, so this moment diagram looks a little bit more complicated than the one that I had before. These moment equations. And let me see if I can simplify this even more. I forgot to plug in values for the reactions here. But I end up getting m of x equals negative wx cubed on 6l plus wlx on 2 minus wl squared on 3. And this is my simplified moment equation. Now we can check this quite easily. I'm starting here, right? The moment at my pin at the roller should be 0. So when I'm checking this, an easy check is that m at L, right, because I have to go L length down, should be 0. And if I do this is going to cancel out. Everything's in terms of WL squared. And I get negative 1 over 6 plus 3 over 6 minus 2 over 6 WL squared. And this goes to 0. I get 0. And that is good. So everything is good. Okay, so that is your moment equation. Now, I'm not going to do the diagrams because we need to have something to grade, but your deflected shape for this problem should look a lot like the deflected shape that you got for the last problem. The only difference, and it's not very easy to distinguish the two of them, if we were just to look at it by inspection, if we were trying to go backwards, if you were given the deflected shape and you were trying to derive the moment diagram, you would just know that there was some distributed load on the vertical member. You would not know if it was a triangular up, triangular down, if it was rectangular. At least with a hand drawing. With computer drawing, it is much easier to tell, but a hand drawing, like, it's just not easy to compare an x to the 5th function versus an x to the 4th function manually. So with that, don't be concerned if you get a deflected shape diagram that's very similar to your deflected shape diagram in number 1. And oh yeah, you don't need to drive equations for the deflected shape. You're just supposed to draw the deflected shape. Okay, but yeah, so I'm gonna go into problem. I'm gonna skip problem 3. I'm not gonna go into problem 3 because I think that is much easier than the ones we did before because it's a rectangular load. I will go into problem 4, however, and that'll be the next video.